All right, so pick out the best answer. All right, so what do we have? We have an artificial satellite moving at a constant speed in a circle around the Earth. Is it accelerating? Yeah, it's moving at a constant speed, but the direction keeps on changing, right? So which means that, of course, it is accelerating. So the best answer is going to be yes, because the direction of motion keeps changing. It is accelerating. Now we got a definition for acceleration. Acceleration is how fast you speed up, how fast you slow down, and how fast the direction changes in time. So it's a combination of speed and direction. So instead of saying how fast you speed up, slow down, or change direction, the summary statement is how fast the velocity changes in time. So how fast the velocity changes in time becomes the proper definition of acceleration. So what is the proper definition of acceleration? Proper definition is how fast the velocity changes in time. How fast you speed up, how fast you slow down, and how fast the direction changes in time. Okay, so what's acceleration? Acceleration is how fast you speed up, slow down, or change direction. What is the proper unit for acceleration? We haven't done that. G is the acceleration expressed in terms of your own body weight. So 7 G's feels like 7 times your own body weight. 12 G's feels like 12 times your own body weight, and so forth. Question number 4, the direction of the unstrapped objects inside accelerating vehicles like cars. Your body's going to move in the opposite direction of the acceleration of the vehicle. So speeding up, is that acceleration? Absolutely it is, because the unstrapped objects will move in the backward direction. Slowing down, is that acceleration? Yes, it is, because the unstrapped objects will move in the forward direction. And what if you're moving at a constant speed while changing direction? Once again, that's acceleration, because once again, the unstrapped objects will move in the opposite direction of the acceleration of the vehicle. So what's the proper definition of acceleration? It's speeding up, slowing down, and changing direction. How fast you speed up, how fast you slow down, and how fast you change direction. Okay, so let's move on to the mathematics of this. It's how fast the velocity changes in time, so that's what acceleration is. All right, so initially, this is how fast the object is moving. That's the initial velocity. This is getting displaced on the x direction. And here's the velocity at a later time. This thing is speeding up, meaning that it's accelerating in the forward direction. So its velocity is changing within this time period. So that's how fast the velocity changes in time. So you go from an initial velocity to a final velocity within this time period. And this becomes your acceleration. How fast the velocity changes in time. VO is your initial velocity. V is your final velocity. T is time. Is your acceleration. Time is going to be in terms of seconds. Velocity is going to be in terms of meters per second. So the acceleration. All right, so this is meters per second, and this is seconds. So which means that this is going to be meters per second squared. All right, so the acceleration is going to be meters per second squared. We're not going to worry about expressing acceleration in terms of meters per second squared. Instead, we'll express it in terms of G's for safety reasons. So the acceleration is going to be expressed in terms of G's. 1G roughly, okay, so if you see a wiggle like this, it's an approximation. 1G roughly is 10 meters per second squared. All right, so that's what we will get to use. We will get to use for acceleration. All right, so acceleration is how fast the velocity changes in time. So you go from an initial velocity to final velocity within this time period. So this acceleration is how fast you go from this to that within this time period. So these accelerations, these velocities, are they average or instantaneous velocities? And this time, what does that time refers to? All right, so VO is your initial velocity. This is your final velocity. VO represents how fast you're moving right at this point, guys. All right, this is your speed at this time. So that's your instantaneous speed. That's your measured speed. V is your final velocity right at that time. So VO is your initial measured velocity. This is your final measured velocity. And T is the time it takes time between measurements. All right, so T is the time between measurements that you're looking at. So everything that you see here on the right-hand side are measured. On the left-hand side, this is going to give you your average acceleration. So this represents your average acceleration. Average acceleration, average acceleration, average acceleration. Instantaneous velocity, and measure time. So stuff on the right, measured. Stuff on the left is average. Oh, the formula doesn't show, that's fine. All right, pick out the best answer. If the velocity keeps changing, change in velocity in time is the definition of acceleration, so which means that the object is always going to be accelerated. And D is the best answer for that one. So acceleration, for safety reasons, will be expressed in terms of G. 1G is the same as your own body weight, which is roughly about 10 meters per second. So MK as unit system is meters, kilograms, and seconds. Acceleration expressed in terms of MK as unit system will be meters per second squared. So the best answer is C. Now acceleration is a vector, meaning that it's got direction. If it's to the right, it's going to be positive. If it's to the left, it's going to be negative. Positive acceleration simply means that something is speeding up. So if we talk about acceleration being positive, that's positive acceleration, which means that the object is speeding up. Notice that the acceleration that points from smaller to the larger of the velocity, so it's speeding up. If it's negative acceleration, it's slowing down. So positive acceleration denotes speeding up, negative acceleration denotes slowing down. All right, so during acceleration, only the speed changes, the direction of motion changes, only the average velocity changes, only the instantaneous velocity changes. All right, the best answer is your instantaneous velocity is changing. How fast the instantaneous velocity changes in time is what the acceleration is. So D is the best answer in this case.
1950s year.
So 7 to 12 G's up to a few minutes, you can survive. But the car collisions usually last for a fraction of a second. Can you survive up to 15 G's, 20 G's, 30 G's, 40 G's, 50 G's? What is the maximum that you could be exposed to and still be able to survive? The car companies wanted to know. So they decided to conduct some experiments on that. The most famous experiment which was conducted is known as the John Stapp experiment that took place in 1954. He actually volunteered for this one. So they took this guy, they strapped him onto a
1950s, years before the Pinto or Corvair. Little was known about the essence of a collision, how much force the driver could withstand. To find out, a seemingly lunatic experiment was carried out in the New Mexico desert by the U.S. Air Force in 1954. Scientist John Stapp strapped himself onto a rocket sled to boldly go where no man had gone before.
He started the countdown. 10, 9. Adrenaline comes in and the heart begins to beat a little faster. Then, just as he reaches 0, you get this enormous ram against your back. And you feel totally helpless. You'd be given the biggest kick that could be delivered.
Stapp had been propelled at a speed of 632 miles per hour and stopped in 1.4 seconds.
All right, so those of you guys who don't know, 632 miles per hour is about 80 miles per hour faster than a commercial airliner. So this guy was already moving 80 miles per hour faster than a commercial airline at the time they put the brakes on. 1.4 seconds is this long. So imagine that you're on a commercial airliner drinking your coffee or doing whatever it is that you guys do. And then they bring the airliner to a stop within 1.4 seconds. What does that feel like? How many G's is that? Is that even survivable? Let's find out. All right, so this is the John Stapp experiment. John Stapp experiment. Okay, so go to modules one more time. And then this time find the problems. Open up the problems. All right, so problem number 2 is the one that we're looking at. It says 1.25 seconds. Its reality is 1.4 seconds. And so let's figure out the acceleration. So this is being done in 1954. He was brought to a stop from 632 miles per hour. All right, so the John Stapp experiment, 1954. He was initially going at 632 miles per hour, and he was brought to a stop within 1.4 seconds. So what was his acceleration expressed in terms of G's? The first thing we need to do is we need to express this in terms of the metric units. So speed needs to be expressed in terms of meters per second. So we do the conversion, and we get a number for it. Next thing is to come up with the right formula. So change in velocity in time is going to give us the acceleration. The final speed is 0. And then now plug the numbers in terms of the numbers, in terms of the metric units. It's going to give us an answer in terms of meters per second squared. All right, so the square is missing there, so you have to go back and adjust it. And so now we're expressing in terms of G's, so this is 20 G's. So he was experiencing 20 G's for 1.4 seconds. So the question is that survivable? So John Stapp was exposed to roughly about 20 G's for 1.4 seconds. Did he die or did he survive?
No one has ever undergone such a test before or since.
Obviously he's alive.
I couldn't see anything.
Except he couldn't see anything.
And I was looking
And there's a reason why he couldn't see anything.
around and, you know,
Because his retinas got detached. Is that a big deal? Not necessarily, guys. It doesn't have to be a big deal. The only thing you have to do is just push him back in. Check to see if it works. If it doesn't, you need to be taken to a hospital. And eventually you should recover. If not, they have to do a surgery on it. Sometimes the boxers experience
I
that.
was beginning to think about seeing
So 20 G
my dogs in white
for 1.4 seconds.
canes. And I was thinking to myself, now I've paid my dues. I've gotten there. And I've shown them what they want to know. And from now on, their life is going to...
So 20 G's for 1.4 seconds. Survivable or not? Alright, so 20 G's for 1.4 seconds. Evidently it's survivable. Not only is it survivable, it's also survivable very easily. John Stapp kept volunteering for these experiments, so the question is why? Why would you volunteer for something like this if the outcome is uncertain? The reason why he volunteered for it, because he was in charge of these experiments in the first place. He was a medical doctor. They advertised. No one was interested. He conducted experiments with animals, cats, dogs, mice, whatnot. And all of them ended up doing well, so he figured that it was going to be fine as well. All right, so 20 G's, it was survivable. And then at 21 G's, 22 G's, 24 G's, everything was survivable. At 25 G's, they noticed that after 25 G's, you start breaking bones. Smaller bones in your body will start to break. And it starts to become a problem after 25 G's. So what do we know? You can survive up to a few seconds. You can survive up to 20 to 25 G's for a few seconds. So that becomes the conclusion, main conclusion. So that